So first of all, can you all see my screen? So it seems that, thank you very much. So there will be 7 lectures on magnetism. If you are interested in the chapters that are covered in the textbook, so it will be on the stairway, it will be to chapter 28, 29, and part of chapter 30 and 31. So today we're going to talk about magnetic forces and fields. So in this lecture, there will be 3 main points that will be discussed. So first of all, what is magnetism and how it was discovered? Then we'll talk about the notion of magnetic fields and magnetic lines. And finally, we'll talk about motion of charged particle in a magnetic field. So if you have questions during the lecture, please turn on your microphone and ask the question directly. I will try to make pauses quite regularly so you have time to ask questions. So let's start with the first part. So as I told you today, so this is the 3 parts will be covered. And by the end of this lecture, you should be able to recall the 4 main properties of magnetic field line, state the equation for magnetic force on a moving charged particle, and finally recognize the formulas for gyro radius and orbital frequency. So obviously I will explain you what is a gyro radius and what is the orbital frequency when it comes to that. So first of all, before we actually jump into magnetism, I need to remind you what is an electric current. So you just finished the module on electricity with Professor McWilliams, and you have seen, like, if you put charged particle in an electric field, you can make those particles move. So an electric current, I mean, you can see this as like a water flow current in a pipe, for example. Here, the electric current is just defined as the rate at which charges, so here delta Q, are flowing through a surface A in a time delta T. So here in this schematic here, you have like this circular area and you have like positive charge flowing through it. And if you count the number of charge flowing through this surface in a time delta T, you can define the average current through this surface in this time delta T. So when delta T goes to 0, so we take the limit delta T goes to 0, then you can define the instantaneous current as the derivative of the charge going through the surface with respect to the time. So you might have dealt with electrical current already in term 1. So the unit of electrical current is the ampere, which is the same as Coulomb divided by second. Any question on that? No, so let's continue. So in a wire or like any other kind of conductor, so the electric current will be like caused by an electric field that you apply at each end of the conductor that will force the charge to move. So if your charge carrier are like positively charged particles, they will move in the direction of the electric field. If those are electrons, so negatively charged particles, such as in a metal, for example, the electron will move in the opposite side of the electric field. So, for example, in this case, the positive charge here will move rightwards because the electric field points to the right, and the electron, negative charge, will move leftward. See, like the current I always point in the same direction as the electric field. All right, so you see like a flow of positively charged particle in one direction. Mathematically, it's exactly the same as a flow of negatively charged particle in the other direction. Okay, the minus sign will cancel each other, so you end up with a current in the direction of the electric field. Any question? No. So let's continue. Then the last slide on electrical currents. So in a metal, which is a conductor, So the motion of the charge carrier is a combination of a random thermal motion and a steady drift driven by the electric field E. Okay, so electrons in a conductor, so your conductor is not at zero temperature, is not at the absolute zero, so your free electron, your charge carriers, they always have a thermal motion. So that's what you see here, okay? They will move in random direction, and they abruptly change direction because they collide with the atoms that make the metal. So like the metal atoms are organized in a crystalline structure, and the electrons, they can jump from one atom to another. And you can see that as elastic collision with the atom. So here, for example, in this picture, you can see like there would be an atom right there. There would be another atom right there, like basically at each corner of the trajectory. That's because you have a collision with an atom. Now, if you add an electric field, so here, for example, an electric field pointing to the left, then your electron will move to the right, okay? So they go in the opposite direction as the electric field. And because of that, even though they still have collision, they will have a drift velocity, which is induced by the presence of this electric field. So now there is order of magnitude. So in a conductor at room temperature, so the wire, for example, that is connecting the light bulb in your kitchen to the switch, the drift velocity, the magnitude of the drift velocity will be of a few millimeters per second. While the random motion here, which I will call V thermal, will be of the order of 10 to the 5, 10 to the 6 meter per second. So the thermal motion is much, much higher than the drift motion induced by the electric field, but it is still enough to like power apparatus and so on, because you just need a small drift to actually have a current. All right, so now that we have a reminder on currents, let's jump into magnetism. So first of all, what is magnetism and how it was discovered? So in the 19th century, physicists discovered that magnetism is closely linked with electricity. Okay, so that's why I started with remembering what is re-explain you what is electric current, is because when you have moving charge, so an electric current, that produces a magnetic field. Okay, so this was discovered by Ørsted and Biot-Savart. Magnetic fields affect moving charge. So this was discovered by Davy, and that's what we will see in later on in this lecture. Changing magnetic fields can create electric fields and currents. So this we will see in lecture 11 and 12. And this is what we call Faraday's law. And ultimately, the source of any magnetic field is an electric current, whether it's due to the microscopic motion of charges in a wire or the motion of charges at the atomic and subatomic scale. So in an atom, okay, so you have like the nucleus, which is positively charged, and you have a cloud of electrons around it. Okay, so those electrons, they are mobile, okay, they move all around those nucleus. And they can, because of that, they can create magnetic moment for each atoms, okay? And for special kind of atoms, like for example, iron atoms, that's they have a very strong permanent magnetic moment. And if you make a crystal of iron atom, you can create permanent magnet. All right, so now I will just show you a quick demo for.
I want to show you how a magnetic.
So can you hear the video? Can you see the video, by the way?
Yeah.
All right, thank you.
Needle responds to a current. I have here a wire through which I'm going to run a fabulous amount of current, something like 300 amperes. And you're going to see that wire there. I'm going to get my lights right. Let me see how I want it to go. This is the way I want it to go. To get you optimum light there. When I draw a current, here you see the magnetite, we call it a compass nowadays, and it's lined up in the direction of the magnetic fields of the Earth. We're going to run 300 amperes through here, and it will change the direction. It will change the direction, which is there's going to be a magnetic field around the wire like this, so it will go like this. The current that I run is so high that things begin to smell and smoke within seconds. The battery is not going to like it when I draw such a high current. I can therefore do it only for a few seconds. So this compass will swing in this direction and it starts to oscillate. I can't keep the current so long that it stops the oscillation. So I will stop it by hand and convince you that that's really the equilibrium position. So if you're ready for that, so we got now connection. Watch it. 3, 2, 1, 0. There it goes. And I will stop it. The current is still going. That is the equilibrium position. And I will stop the current. And now I will reverse the current in the opposite direction. And now you will see that it swings backwards. It's 180 degrees in a different direction. 3, 2, 1, 0. There it goes. I will stop it. Few seconds, that's the equilibrium position, and I let it go.
All right, so what you've just seen here is basically a demonstration by Professor Lewin at MIT, where by drawing a very large amount of current in a wire, you actually create a magnetic field. So this was a huge discovery in the 19th century. Like, you can actually create magnetic fields just by flowing current. Okay, so of course you all know like permanent magnets. Okay, you have those like you can have those in on your fridge, for example, and those are created by a special kind of material, what we call ferromagnetic material, that we will be discussing later on in this module. All right, so let's discuss about magnet now. So if you chop a magnet in two, you will always have two poles, okay? So you will have one north pole and one south pole, okay? And that is why, like, when you take a needle, a magnetic needle, the one end will always point towards the geographic north of the Earth. So, okay, with the magnetic north, sorry. So the magnetic north is somewhere in northern Canada. And because of that, we call this the pole that points toward the north pole of the magnet. That implies that the south pole of the Earth magnetism is actually at the geographic north pole, because like pole north attract each other, repel each other. Sorry, north is repelled by north, south is repelled by south, and unlike pole, north-south attract each other. So you can make a parallel with electricity, where like charge repel each other and opposite charges attracted each other. Okay, so the main difference between electricity and magnetism here is, in electricity, you can have like single charge, so what we call charge monopole. Like an electron, for example, it's just a negative charge. A positron is just a positive charge. A proton is just a positive charge. For a magnet, you cannot isolate the two poles, okay? If you cut a magnet in half, you will end up with two magnets that each have two poles, okay? There is no way to isolate one pole in a magnet. So if I take a bar magnet like that, so we have north, south, I cut it in half like that, and I will obtain two magnets, one north-south like that, and another north-south like that. Okay, and if you let them go, I mean, they will attract each other, and they will glue here, and you will end up with the original magnet with one north pole and one south pole. Any question? No? So let's move to the next slide. So the north pole of a compass needle points north because the Earth's south magnetic pole is in northern Canada. So here you have a representation of the Earth. So the Earth's magnetic field, you can like image it as if you had a bar magnet that's passing through the center of the Earth, and the south pole of the bar magnet is actually pointing north, and the north pole of the bar magnet is actually pointing south. So then it creates magnetic field lines that goes from the north pole to the south pole of the bar magnets that is inside the Earth. Okay, and the compass needle will align with this magnetic field. Therefore, the north pole of your needle magnet will align, will point north geographically because it's attracted to the south pole of the magnet that is inside the Earth, of Earth magnetism. And the south pole of the magnet is of the needle magnet is attracted to the north pole of Earth magnetism. Okay, so those magnetic field lines, they actually have huge implication because, as we will see, magnetic fields are able to influence the trajectory of charged particles, so they can deflect charged particles. And the solar wind, which is mostly composed of charged particles like proton and electron, can be deflected by Earth's magnetic field, and then they will collide with the atmosphere and produce like northern line or auroras. And being in Saskatchewan, if I show you this kind of picture, that's something you probably have seen at night here. And all this light here, so like the northern light, is created by the solar wind colliding with the atmosphere. And why so? It's because the magnetic field lines, the magnetic field of Earth is deviating those charged particles into the atmosphere. And then those charged particles interact with the oxygen and nitrogen atom. They excite them, and then they can emit light that you can see with your own eyes. Any question? All right, let's move forward then. All right, so now let's discuss the properties of magnetic fields and magnetic lines. All right, so magnetic fields are represented by magnetic field lines with the following properties. So the magnetic field is tangent to the magnetic field lines. The magnetic field strength is proportional to the line density, and the field line cannot cross. Otherwise, cross point will have two values of the magnetic field that we write B vector. Okay, field lines form continuous closed loop directed from the north pole to the south pole. So as you can see, this point number 4 is the only difference between electric field line E and magnetic field line B. Okay, for electric field lines, you have a start point or an end point. Okay, so an electric field is pointing from the positive charge to a negative charge. A magnetic field line, it's a loop. Okay, there is no end point, no start point. Okay, and it's because we can only have magnetic dipoles. Okay, so compass needles always point along the direction of the magnetic field lines, so they can be used to visualize magnetic field. Okay, so here there's some illustration. So here you have like bar magnets. So north pole here, south pole here. And if you draw the magnetic field line, you start from the north pole, and you end up in the south pole. But actually, if you want to complete the loop, like for example here, your magnetic field line can be completed inside a bar magnet like that. Okay, so it's a loop. If you approach two bar magnets, so here you have the north pole and the south pole, then the magnetic field line goes from the north and end into the south. And if you have two bar magnets, north pole, the magnetic field line repel each other, and that's how the magnetic field line will look like. So you can do that in experiment. So here you have a bar magnet, north-south, and here we use like iron filling. So iron filling, you can see like each bead of iron as a small magnetic needle, and they will align themselves with the magnetic field. Okay, so as you can see here, you have the schematic representation of the magnetic field lines, and here you have a direct visualization with experiments. Okay, and as you can see, the schematic reproduce very, very closely what you see in experiment. So here's a question for you. So from the property we just discussed, for this situation here on the left, in what region is the magnetic field the strongest? So if you have an idea, just turn on your microphone and.
At the two ends?
Yes, exactly, at the two ends. As you can see here, the density of magnetic field line is very high. Okay, so therefore you have a very strong magnetic field right, very close to the magnet. And intuitively, that's what you expect. I mean, you all have played with magnets, and you know, like, I mean, when you want to stick your magnet to a piece of metal, like for example, a magnet on your fridge, you have to come close to the magnet so for the force to be strong enough to actually feel it with your hand. That's because the magnetic field is very strong only when you are very close to the magnet. So now you have the experimental picture for like the 2-bar magnet with north and south pole facing each other. And you can see again, like the magnetic field line, the experimental magnetic field line strongly resemble what you could expect just from a raw calculation. So again, here's a question. So if you see my pointer, so is the magnetic field stronger at the red dot or stronger as an orange dot?
Orange dot?
Yes, it will be stronger as the orange dot. As you can see here, the density of magnetic field line is stronger right in between the two magnets. So at the orange dot. All right, finally, the last situation. So now we have two north poles facing each other, okay? What is the value of the magnetic field here in the green dot here on the picture, which would be here, right there? What do you expect for the value of magnetic field?
Would it be 0?
Exactly, it will be 0. So the thing is, each magnet is creating its own magnetic field. So like in blue, I will draw the magnetic field of this left magnet. So it will be like that. And in light green, I will draw the magnetic field of the right magnet, sorry, and it will be like that. And the total magnetic field is the sum of the two magnetic fields. Okay, so the sum here is obviously 0. Okay, so now if we go back to the list of things, sorry, not here, right there, the magnetic field is tangent to the magnetic field line. So if I go back to the example here, if I just want to plot the magnetic field at different points, so for example here, I will choose here, here, and right there. So here's the magnetic field. If I just plot the vector, it will be like that. Here it will be like that. Here it will be like that. And here it will be like that. Okay, so always tangent to the magnetic field lines. Any question on this part?
Hi. When you were discussing how the loops were completed inside the magnet, is there a magnetic field then inside the magnet itself, or?
Yes, so a bar magnet is made of material what we call magnetic, which is just an iron oxide that has a permanent magnetic moment. So we'll discuss that in later in the course, what it means to have a permanent magnetic moment. What it means is anywhere in this bar magnet, you have a magnetic field. Okay, so when you complete the magnetic field lines, that's how they will look like. Okay, so, and you can see that just by making this experiment in your head. Like if you cut this bar magnet, you end up with two magnets. Okay, it's because the magnetic field is there. Okay, you have many small magnetic dipole that create this long bar magnet. Okay, and each atom of this bar magnet creates its own magnetic field. So you have a magnetic field inside the bar magnet. Make sense?
Yeah, okay, thank you.
All right, so now that's addition of magnetic field. So here in the example, you've seen like you have example with two magnets. So you're not limited to two magnets. So if you consider a point P anywhere in space, and you want to find what is the magnetic field at this point, you have to consider all the magnetic field that are created by different devices. So for example, you can have a magnetic field B1 created by a magnet or an electric current, and a second magnetic field B2 created by another magnet and an electric current, and a third, and so on and so on. And the total magnetic field at point P will just be the vector sum of those different magnetic fields. So if I make an example, so for example, I have a magnet like that, and I have another magnet like that. For simplicity, we'll just consider like you have a north pole here, south pole here, south pole here, and we'll consider point P right there. Well, what is the total magnetic field? Well, I just have to, so this is B1, so this is magnet 1. And here I have B2 created by magnet 2. And the total magnetic field is just the sum of the two. So this will be B total. Any question on that?
Yeah, sorry, but wouldn't the field lines, the vectors, point away from the North Pole?
Exactly. So I will correct that. And I don't want to redo everything. So that will be a south pole here, a south pole here, a north pole here, a north pole here. Thank you for noticing this typo. Other question? No, so now let's dive in something that is slightly more complicated, which is the motion of a charged particle in a magnetic field. Okay, so before we jump into that, there is something you've seen in math, which is called the cross product. Okay, so the cross product is you take two vectors and you end up with a third vector. So to find the direction of the vector, you can use the right-hand rule. So for example, if you try the cross product of A and B, that will give you a vector C. You have your index pointing into the direction of vector A, your major pointing in the direction of vector B, and your thumb of your right hand will point in the direction of A cross B. Okay, so if you make operation on unit vectors, so Cartesian basis, so I hat cross J hat will give you K hat, J hat cross K hat will give you I hat, and K hat cross I hat will give you J hat. And if you reverse the operation, you end up with a minus sign because the cross product is anti-commutative. Okay, you can just find this by playing with your right hand, and you see like if you go like that, and if you reverse the operation, you obtain the reverse vector. Okay, so if you have the coordinates of the different vectors, the coordinates of the cross product are given by this formula that you can find in the formula sheet on the Canvas website. And the magnitude of the cross product is just the magnitude of A times the magnitude of B times the sinus of the angle between the two vectors. So one very important property of the cross product, and this will be very important when we are considering like the action of magnetic field on charged particle, is the result of a cross product is perpendicular to the two original vectors. So if C is a cross product of A and B, then A is perpendicular to C and B is also perpendicular to C. All right, any question on the cross product before we go further? No, so you should normally have seen that in math already. And it's very important you understand how to use it. So I will now tell you why. Because in a magnetic field, so if you have a magnetic field of strength B, then you have a magnetic force created on a charge Q moving at a velocity V. Okay, so V is a vector here. then the magnetic force will be always perpendicular to both the magnetic field and the charged particle motion, and is defined as the magnetic force F. So I will add an index B equal to Q, so the charge multiplied by the velocity vector, cross product with the magnetic field. Okay, so that's when there is only a magnetic field. Of course, you can end up with situation where you also have an electric field, and then the total force, which is called the Lorentz force, is the addition of the electric force. Here, QE, this is the electric force, and the magnetic force, which is this. Any question? No, so let's move on. So now if you just want to calculate the magnitude of the magnetic force on a moving point charge, then you have to obviously apply this formula, and that will give you the magnitude of the charge, so you don't care about the sign, times the magnitude of the velocity, times the magnitude of the magnetic field, times the sign of the angle between the magnetic field vector and the velocity vector. Okay, so if you go back to the formula here, and if you remember your math classes, you know, like if you calculate the cross product of a vector with a vector parallel to this cross product, the cross product will be 0. So that is very important for magnetic field. What does it mean? It means that if you move parallel to the magnetic field, you will not experience a magnetic force. Okay, so if, for example, if you have a magnetic field like that, and you are moving like that, then you will have a magnetic force. Okay, but if the velocity is like that, for example, v2, which is just reverse the direction of the magnetic field, then the cross product will be equal to 0. Therefore, you don't have any magnetic force. So sometimes it's good to remember that, because if you end up with a question where you just have, like as a given, like you have a magnetic field in the k direction with whatever intensity, and you have a charged particle, for example, an electron moving in the minus k direction with whatever velocity, you don't need to do any calculation. You just say, okay, the velocity vector and the magnetic field vector are parallel, therefore there is no magnetic force. Okay, and you don't have to try the entire set of calculation, like for example that, to end up with a 0. Okay, because just by knowing that if you have two parallel vectors, the cross product is 0, you will save a huge amount of time. So now let's talk about the unit of the magnetic field. So the unit of the magnetic field is a unit of force divided by the unit of charge divided by the unit of velocity and the unit of sine theta, which has no unit. So you end up with Newton divided by Coulomb times meter per second, which is the same as Newton divided by ampere times meter. And this is what we call a Tesla. So why Tesla? So this comes from Nikola Tesla, a Serbian physicist who was a pioneer in studying like electricity and magnetism. All right, so sometimes it's much better to have an intuition of what is the direction of the magnetic force instead of doing long and lengthy calculation. So the method you have to use is what we call the right-hand rule. So there's two ways to do it. So method 1, and then I will go to method 2. So basically what you do is you curl your fingers from V to B with your right hand. So there's a direction like the example here. And then the force will point along your right hand thumb. So if the charge is positive, then the force is exactly in the direction of your thumb. If the charge is negative, it's in the opposite direction of your thumb. There's another way to do it, which is exactly equivalent. So with your right hand again. So if you point your thumb in the direction of the velocity and your finger in the direction of the magnetic field, then where the force, if Q is positive, then the force, the magnetic force, will be in the direction you would push with your palm. If the charge is negative, then the magnetic force in the direction opposite to the direction you would push with your palm. Any question on that?
Sorry, could you please illustrate this visually, like with your hand or something?
Yes, so this is my right hand. Okay, you see my hand on the video?
Yep.
All right, so this is my right hand, and let's say I have an electron that is moving along my thumb, so the velocity towards the ceiling. And the magnetic field is pointing into my screen, okay, so towards you from what you see in the screen. Then the magnetic force will be either pushing in this direction or in this direction. So an electron, is it positively charged or negatively charged?
Negative.
Negative.
So the force will be opposite to my palm, so in this direction. Okay, so be careful, always use your right hand. Okay, if you don't use your right hand but you use your left hand, then you get a wrong answer. Okay, so it's just a question of practice. Okay, so choose whatever you prefer, either method 1 or method 2 for the right hand rule, but this will save you a lot of calculation, because just by using the right hand rule, you will know the direction of the vector, of the final vector. I mean, with the right hand rule, you cannot calculate the intensity, the magnitude of the final vector, but you already have the answer about the direction. Okay, so that's a very quick way to get at least half of the answer without doing any sort of math. Okay? All right, so now a bit of convention. So as you've seen here, like when we deal with magnetic field, we have no choice but work in 3 dimensions. Okay, so a screen or a piece of paper or a blackboard is obviously 2-dimensional. So we need a way to draw 3-dimensional vectors in a convenient way. So what we do is, the convention for vector out of the page is a circle with a dot in the middle. And for a vector pointing into the page, it's a circle with a cross in the middle. So I will illustrate this with a video. So that should be there.
I hate commercial.
No, that's not this one.
If I have a current, a wire, let's say the wire is perpendicular to the blackboard, and the current goes into the blackboard.
So here's a current,
I
but
put a
it
cross
could be a
in there.
magnetic field.
If the current comes out of the blackboard, I put a dot there. And there is a historical reason for that. You've always talked about vectors in 1801 and in other courses, but you've never seen a vector. And I'm going to show you a vector. This is a vector. And this is when it comes to you. That's when you see a dot. And this is when it goes away from you. That's when you see a cross. So this current, well,
all right, so that was illustration of what is a vector. So just remember, like if you have like this arrow image into your head, so when the arrow is coming to you, you only see the tip of the arrow, that's why it's a dot. And when the arrow is going away from you, you only see the back of the arrow, so you only see a cross. Okay. So now let's make some, let's do some classic example. So let's try to calculate what would be the magnetic force on an alpha particle moving in a magnetic field. So an alpha particle is just the nucleus of a helium atom. So it has 2 protons and 2 neutrons. And because it has 2 protons, it has therefore a charge of twice the elementary charge, which will be here equal to 3.2 10 to the minus 19 Coulomb. Okay, this alpha particle will move into a uniform magnetic field B, which is defined as B vector equal 1.50 Tesla along the k hat vector. And we want to find the magnetic force on the alpha particle in 4 cases. Okay, case 1, when the velocity vector of the alpha particle is 5 10 to the 4 meter per second along I hat. Case B, minus 5 10 to the 4 meter per second along J hat. Case C, 5 10 to the 4 meter per second along K hat. And finally, a combination. So 2 10 to the 4 meter per second along I hat, minus 3 10 to the 4 meter per second along J hat, plus 1 10 to the 4 meter per second along K hat. All right, so let's try to solve this. So what is a given? So the given is that alpha particle with charge Q equal 3.2 10 to the minus 19 Coulomb. Okay, we know we are in a magnetic field B, which is equal to 1.50 along K hat Tesla. All right, and now we are interested in case A, where we know like the velocity of the alpha particle is equal to 5 times 10 to the 4 meter per second, and it was along I hat. So how do I calculate the magnetic force? So I use the formula for the magnetic force. So FB is equal to QV cross B. So before we do the calculation, what will be the direction of the magnetic force? See, you have the velocity along I hat, the charge is positive, and you have the magnetic field along K hat. So without calculation, just using the right hand rule, what will be the direction of the magnetic force?
Towards you.
Minus J. Oh, sorry.
Yes, it will be along J. Okay, like for example, if I put a Cartesian basis like that, so my unit vector I, J, and then I have K hat coming like that. So you have I hat cross K hat, and this will give you something along J. Okay. Now, if you use the right hand rule, will it be plus J or minus J?
I think minus.
Yes, minus J. Okay. K, you use, so V in this direction, K pointing towards me. So if I look, it's a bit hard to see here, but the force vector that correspond to my major finger points downwards, so in the minus J direction. So just with the right hand rule, we know that will be along the minus J direction. Okay.
So
now,
just with the right hand rule, we can like solve for the direction.
Yes.
Okay.
So it's a question of habit. I mean, like you have to practice, but if you become good at practicing with your right hand, you can always find the direction of the force if you know the direction of the velocity and the direction of the magnetic field. And of course, the sign of the charge, positive or negative.
So K is now towards and away from us. So positive K is towards you, and then negative K is away from you.
Yep.
Okay.
Yes. So you see, I draw it a circle with a dot, so it's coming out of the page.
Right, yeah.
All right, so now let's do the calculation. So FB equal, so 3.2 10 to the minus 19 Coulomb times V, so it's times 5 times 10 to the 4 meter per second I hat cross 1.5 K hat Tesla. So I can rearrange this. So FB is equal to 3.20 times 10 to the minus 19 Coulomb times 5 10 to the 4 meter per second times 1.50 Tesla times I hat cross K hat. Right-hand rule, this you immediately know that gives you minus J hat. So if you do the calculation, you will end up here with FB equal to minus 2.40 10 to the minus 14 J hat Newton. Is it clear for everyone? All right, let's try to do the second case now. So we just
sorry, could you just walk us through how you like the exact process for the right-hand rule for that question?
Yep. So let's take this one, for example. All right, so if you remember the question, the velocity was along I hat, and the velocity, the magnetic field was along K hat. Okay, so you take your hand, your right hand, you point it along I hat, and then you curl your finger along K hat. So that was coming out of the screen for me. And you see my thumb is pointing downwards. Okay, so that is giving me directly the direction of the force because the alpha particle is positively charged. Make sense?
Yes, thank you so much.
All right, so let's try to do case B now. So the magnetic field and the particles have not changed, but the only thing that has changed now is the velocity, which is minus 5 10 to the 4 along J hat meter per second. So case B, V is equal to minus 10 to the 4 along J hat meter per second. All right, so without calculation now, what will be the direction of the force? So try using the right-hand rule.
Positive I hat.
Minus I hat.
Yes, it would be minus I hat. Okay, so again, right-hand rule. So along minus J hat, so my finger pointing downwards. Okay, with if I redo the schematic here, so you have I hat, J hat, K hat. Okay, so velocity downwards. Okay, then I have to curl towards me like that, and you see like the force is pointing in this direction, which is in the minus I hat direction. Okay, so no calculation, just using my right hand. I know that the answer has to be along the minus I hat direction. So now I can do the calculation. So you see the number are exactly the same as before, 5 10 to the 4, 1.5 Tesla, 3.20 10 to the minus 19 Coulomb. So the numerics I did here, they're exactly the same. So the value here, without doing any further calculation, because I already know the direction of the force that I will obtain, will be minus 2.40 10 to the minus 14 I hat Newton C minus I hat. Any question on that? No? So let's try to do the third example now. So the given are exactly the same. And now the difference is V is along K hat. Okay, so now C, V is equal to 5. 5 10 to the 4 K hat meter per second. All right, what is the value of FB then?
0.
And why?
Because it's going parallel to the magnetic field.
Exactly. So FB here equals 0 and V parallel to B.
When FB equals 0, do we have to give an explanation in the answer?
Yes, you have to say because V is parallel to B. Okay. And finally, the last case, which is a more general case. So D, if I go back to the text, so 2 along I, 2 minus 3 plus 1. All right, so this one is slightly more complicated. Okay, like you can still use the right-hand rule, but the only thing you know is you also have a combination of I hat and J hat as the answer. Okay, why there is no component along K hat?
Because like B is parallel to B.
Yes, so the component that is parallel to B do not matter. Okay, so here for such a general case, you have no choice but do the entire calculation. So you use the formula FB equal QV cross product with B. So I will put the number in only at the last minutes. So here, this number here, I will call this Vx. This number here, I will call this Vy. And this number here, I will call this Vz. So I can just write Q. So Vx I hat plus Vy J hat plus Vz K hat cross B K hat, where B is just 1.5 Tesla. So now I have to do every cross product individually. So I will end up with QB. So I'm just taking the B out. Vx I hat cross K hat plus QB Vy J hat cross K hat plus QB Vz K hat cross K hat. Okay, so this last term is equal to 0 because K is obviously parallel to itself. So you end up with QB, so I put this as a factor in front of everything. So I hat cross K hat, this is equal to minus J hat, so you have minus Vx J hat. And you have J hat cross K hat, so this is equal to I hat, so plus Vy I hat. So now I can replace by the value. So here you have Vx is equal to 2.0010 to the 4 meter per second. you have Vy, which is equal to minus 3.00 10 to the 4 meter per second. You know the value of Q, you know the value of B, so you can just put all the number in, and you end up with the force, which will be equal to minus 1.44 10 to the minus 14 I hat minus 9.60 10 to the minus 15 J hat, and the unit, it's a force, so it's in Newton. Makes sense for everyone?
That's a quick question. So if the magnetic force was along J hat, then we wouldn't use the -3, we'd use just 2 and 1.
Yes. So if for example, like you change the magnetic you change the magnetic field, and instead of being along K hat, it's along J hat. Of course, the J hat cross J hat becomes 0, and you have to take into account the I hat and the K hat component.
Okay, thank you.
Could you like draw what the sorry, like the right hand coordinate thing looks like, but like on a Cartesian plate, like X, Y, Z? Because I'm finding it pretty hard to understand the IJK kind of right hand thing.
Yeah. Okay. So let's make a schematic in 3D, for example. So you have I hat like that, J hat like that, and K hat like that. Okay, and now you use your right hand. Okay, and you say V is along I, so coming towards me, and I have to curl. I want to curl with J hat, so I have to go like that. Okay, so I'm curling my hand, pointing my finger in this direction, and curling in this direction. Then I will obtain, my thumb will point toward K hat. Okay, so if I use the right hand rule, I get I cross J will give me K. Okay. Now if I cross J hat with K hat, so I have my finger, my hand pointing toward J hat, I curl my finger toward K hat, and you see my thumb is pointing towards me, toward I hat. So if I cross J hat with K hat, I will obtain I hat, just with the right hand rule, okay? Finger pointing toward J, curling towards K, thumb pointing towards me, so on I hat. And finally, the last one, so K hat cross I hat. Same thing, my finger pointing toward to the top, I'm curling towards me, toward a I hat, and you see my thumb is pointing toward J hat. Make sense?
Yeah, thank you.
All right, so now let's move to an application which calls a cross-field velocity selector. Okay, so imagine a device in which you have an electric field that is perpendicular to a magnetic field. Okay, that's why we call them cross field, and they will be arranged as below. Okay, so here, as you see in the schematic, you see a cross. So in what direction is pointing the magnetic field? Towards you or away from you?
Away from us.
Yes, away. So it's pointing into the page. And then you have an electric field here, which is perpendicular to the magnetic field and is going from, so it's a like parallel plate capacitor from the positively charged plate to the negatively charged plate. Okay, now you imagine like you have a charged particle, like I don't know, a proton or an electron, and it enters this region here. And there are some conditions where this particle won't be deflected at all, okay? It will experience an electric force because it's a charged particle. It will experience a magnetic force because it's a moving charged particle, but the sum of the two forces will be equal and opposite in direction. So the vectorial sum will be equal to 0. So the resulting force will be equal to 0. And the particle will continue straight into the apparatus. And this will occur only for a special velocity, Vs, which is the magnitude of the electric field divided by the magnitude of the magnetic field. So let's try to demonstrate this. So let's redo a schematic. Okay, so we add a magnetic field pointing into the page like that, and you have an electric field going in this direction. So I will put this in a Cartesian basis. So I, J, K hat. So as you can see now, the electric field is going along minus I hat, and the magnetic field is going along minus K hat. Okay, so this is a particle that is moving in an electromagnetic field. So the particle was entering the system with a velocity like that, V particle, which was along minus J hat. So if you remember the electricity part with Professor McWilliams, so you know, like the electric force, Fe is just the charge times the electric field. Okay, so here we can write our electric field is E minus E I hat. So here will be just be minus Q E I hat. All right, is that okay for everyone? So now let's write the magnetic force. So the magnetic force, Fb, equal to QV cross B. Okay, so our magnetic field B is minus B K hat, and the velocity is minus V J hat. Okay, so I can write my magnetic force Fb equal to Q minus V J hat cross minus B K hat. Okay, what will be the direction of the resulting magnetic force?
Minus I.
Are you sure?
Yeah.
Positive I?
Positive
No,
I.
positive
Okay.
I.
So before you do your right hand rule, you can simplify the problem. You see, minus, minus, they cancel each other. Okay, so you just end up with Vj hat cross Bk hat, everything positive. So I do like that. So my right hand pointing to the top of the paper, okay, curling toward me, my thumb is pointing along the I hat direction. So the resulting is Q, V, B, I hat, okay? Just using the right hand rule. So now if the particle is not deflected, that means FB vector plus FE vector is equal to 0, which I can just rewrite as minus Q E I hat plus Q V B I hat equals 0, which I can simplify to Q E equal Q V B. The Q does not intervene. And at the end, I have V is equal to E divided by B, which is the formula that was given in the previous slide. Does that make sense for everyone?
Yeah.
All right. So let's move to another example now. So this typical problem you can have in assignment. So we have a proton with a velocity 6 times 10 to the 6 meter per second that moves towards the north in a region where the magnetic field is 1.5 Tesla and points directly up. So first of all, we want to determine the Lorentz force on the proton at the instant it enters the region of the magnetic field. And finally, we want to find the electric field that will allow this proton to move in a straight line. So for this, let's first try to identify the given. Okay, so to your opinion, what are the given in this exercise?
The velocity and the magnetic field.
And the charge of the proton.
Exactly. So that's the three given. Okay. So the first given, it's a proton. The second given is a velocity, 6 10 to the 6 meter per second to the north. And the third given is magnetic field 1.5 Tesla pointing up. Okay, those are the important given of the exercise. So we will use them to solve the question. So given proton, which tell us the charge Q is equal to the elementary charge, so 1.60 10 to the minus 19 Coulomb. Okay, we have a velocity equal to 6 10 to the 6 meter per second north. And we have a magnetic field of 1.5 Tesla up. So we have to work a bit on the given, so we have something that is workable for us. Okay, so what you should do in this case is make a schematic of the problem. So I will say the north is here, the south is here, and the west is here, and the east is here. Okay, so my proton is going like that. I will call this V proton. And my magnetic field is pointing up, so towards me, like that. Okay, so now you have a visualization of the problem. Question A was determine the Lorentz force, so the magnetic force on the proton at the instant it enters the region of magnetic field. So FB on proton. So using the right-hand rule, what will be the direction of the magnetic force? Can you repeat, please?
East.
East, exactly.
East.
Yep, exactly east. Okay, right hand, finger pointing up, curling towards the magnetic field. The force is pointing east. Okay, right-hand rule, force pointing east. All right, so for convenience, I will add like a Cartesian coordinates on this. So I will call. Yes, go ahead.
Is the electric field, is the magnetic field always in the k direction?
So in this example, yes, okay, but it's just example.
Okay.
I mean, right now, for example, let's say I choose this Cartesian basis. So now I have I hat pointing towards me, J hat there, and K hat there. So you see now B is pointing along I hat, not along K hat.
Okay.
Okay, it's just a convention.
Okay, thank you.
So here I have my answer. So the magnetic force FB will be pointing east, so along J hat in this case. So it's QVB in value. So this, you just put what you need. So 1.6 10 to the minus 19 Coulomb times 6.00 10 to the 6 meter per second times 1.5 Tesla. Tesla. And you are along J hat, and you will obtain a magnetic force which is equal to 1.44 10 to the minus 12 Newton, and in this example will be along J hat. All right, now B, now determine the required magnitude and the direction of the electric field that will allow the proton to move with constant velocity through the region. Okay, so in this question, what are the important information you need to remember to solve it?
It would equal 0.
What would be equal to 0?
The field. So,
the electric field?
So that the proton can keep moving, but
yeah,
not sure if it's the field. But.
All right, so before trying to identify, so what you have here is constant velocity through this region. So there is something that is equal to 0, but that it's not the field. So if you remember your dynamics class, this constant velocity mean, the sum of the external force is equal to 0. Okay. Now the other information is we tell you there is an electric field. Okay, and there is still a magnetic field. So what are the external force? Here it just tells you like it should be F magnetic vector plus F electric vector is equal to 0. Okay, that's the information you get from the question. Everybody can see that?
No.
Okay, so read the question again. So it's a follow-up of question A. So now, okay, we tell you that we need an electric field of a magnitude we will have to calculate and direction we have to find out that will allow the proton to move with constant velocity through this region. Okay, so in question A, we just calculate that the proton will feel a force that is pushing to the east, so pushing along J hat. Okay, so if you do not have anything to counterbalance this magnetic force, well, the trajectory of your proton should look something like that. Okay, it's pushed toward the east, so it's not a straight line anymore. Okay, so it's not a constant velocity. It's not a constant velocity vector anymore. Do you agree with that?
Okay, yeah.
So you need another force. So the trajectory is actually a straight line.
Okay, I get it.
Okay, and here we tell you this other force has to be the electric force. Okay, so question B. So I'm just putting the information here. V equal a constant vector. Okay. So before doing any calculation, in what direction should be the electric field?
Negative J.
West.
Yes, exactly. West or negative J. Okay, and why?
Because it's the opposite of the magnetic field or force. FB.
Exactly. Okay, so the proton is a positively charged particle. So the force will be in the same direction as the electric field. So the force has to be along minus J, so it can counterbalance a force which is along plus J. Okay. So the justification in an assignment, it's because Fe equal QE and Q positive. So Fe plus Fb is equal to 0. Okay, and now the magnitude. So,
sorry, please, I don't get what you wrote. Like the V equals the velocity equals what?
Constant.
Okay.
Better? So now if the vectorial sum is equal to 0, that means the magnitude are the same. Okay, so Fe is equal to the magnitude of Fb. Magnitude of Fb that we already have calculated. Okay, it's right there. So we know that the magnetic force, the electric force Fe is equal to QE. And this is equal to the magnitude of Fb. So the magnitude of the electric field has to be the magnitude of the magnetic force divided by Q. Okay, Q we know, this is a charge of a proton. So I can just input this. So I get my electric field, which will be equal to 1.44 10 to the minus 12 Newton divided by 1.60 10 to the minus 19 Coulomb. And I will obtain 9.00 10 to the 6 Newton per Coulomb, which is the same as volt per meter. Okay. How do you feel about the value of this electric field? Is it small? Is it big? Is it medium?
I'm going to say pretty large.
Yes, it's actually huge. Okay, this is like you can create arcing in air with this kind of electric field. So what does it tell you about a magnetic field of 1.5 Tesla? Is 1.5 Tesla a big magnetic field or a small magnetic field?
A big one.
Big?
It's a huge magnetic field. Okay, so just for information, the magnetic field of Earth so I will call this F Earth, B Earth, sorry. So its magnitude is about 50 micro Tesla or 50 times 10 to the minus 6 Tesla. Okay, so 1.5 Tesla, it's like slightly less than 1,000,000 times the magnetic field of Earth. So 1.5 Tesla is a huge magnetic field, and if you go to the hospital because you need a magnetic imaging, the machine, I don't know if you've seen those machines already, they look like huge tube, and you go inside the tube. And so this tube is what we call a solenoid. They're superconductor solenoid, and they are made to create huge magnetic fields that will induce resonances in the atom of your body that then you can measure and image the organs and the bones. Okay, and the magnetic field created in those machines is of the order of 1 to 10 Tesla, depending on the machine. Okay, and those are very, very big magnetic fields. That is why when you take an RMN, you should not have any metal on you. Like if you keep your watch in this machine, your arm will go like boom, and you will destroy your watch and probably break your arm as well. All right, so it's 11:20, so that's the end of this first lecture on magnetism. So we did not finish exactly what I wanted to do today, but we'll finish that at the next lecture on Friday before we move on to the next one. I will be connected for like 10 to 15 more minutes. So if you have questions now, please ask them.
Just a quick question.
Go ahead.
Will you be posting the annotated slides or will they be blank?
They will be blank like it was for Professor McWilliams.
Okay, thanks.
Yeah, my question is, do we always have to state like the coordinates? Because like in the previous examples, we did like the k-hat direction towards us, but in this last example, we did like the I-hat direction towards us. So that kind of like messes up with the final direction of the force. So like, do we always have to state that?
So the direction of the force is independent of how you label your coordinates. Okay, if I have, so now we make a 3D Cartesian coordinate, I, J, K. Okay, you see like, so this is a 3D view, but if I make a planar view, this here is exactly the same as that. I hat, J hat, K hat. All right, this is what we call an orthonormal basis. The direction of the vector, I can rotate them however I want in space as long as I keep their relative orientation. Okay, so this thing, if I rotate it, can become that. I hat, J hat, K hat. Okay, I have just rotated that towards me. Okay, and now if I make it in 2D, that would be something like that. J hat, I hat, K hat. Okay, and this I can rotate now more like that. So I can rotate. So here I've rotated like that. And now I will rotate this. So I want to rotate, yep, around here. And I will obtain this. Which on the paper I can write like that. Okay, so it's just a question of labeling your vector. But now, if I use my right-hand rule to calculate, like to find, not calculate, to find the direction of the force, the name I have given to my vector doesn't matter. Okay, if I say I have a force pointing upward, a velocity pointing upward and a magnetic field coming towards me, that I call the vector calling upward k hat, j hat, or I hat, doesn't matter. At the end, I always find that the force is pointing to the side, to the right side of the paper, okay, for a positively charged particle, independent of the name I have given to the unit vector.
Okay, yeah, I get that. But like the first coordinate system you drew, like the k hat points up and then the j points to the right. And the last one, the j points up and the I points to the right. So like if eventually the force is pointing to the right, like now we have like two cases where the right is on the j hat and the right is on the I hat. So like, do we have to like state that, like draw our own coordinate system when answering questions or something?
Yes, of course. Okay, you have to tell the marker what coordinate system you're using. And you have to use an orthonormal direct basis, otherwise it doesn't work. Okay, so if you normally you have seen in math like vector coordinates, so use the one you're at ease with. Okay, if you prefer this one, for example, if you prefer this one, always use this one. If you prefer this one at the bottom, always use this one. Okay, the name you give to the vector, if they're not imposed onto you because it's a given of the exercise, it's a choice, it's a personal choice, and you choose the one you are more at ease with.
Okay,
is there
thank you.
one that you prefer for us to use?
I don't mind. I can switch from one to the other independently. Okay. Personally, I don't mind. You choose an orthonormal direct basis that you are confident to use without trouble. Okay. If this one, the top one, makes more sense to you, use the top one. In the bottom one makes more sense to you, use the bottom one. I'm pretty sure no one will use the middle one because this, I mean, even if it's mathematically valid, it's a choice that is weird.
Okay, thank you. I'm sorry, I have one other question. So the last example we solved, like the part A, we're asked to find the Lorentz force. But I think the formula we used was for the magnetic force. So how does that relate?
So that's I will probably correct this in the post-it slide. So the Lorentz force, most of the time, it's a combination of electric field and of electric force and magnetic force. So that is what is written. I have to find it again right there. Okay. Combination of electric force and magnetic force. In many textbooks, sometimes they call Lorentz force the magnetic force as well, because as you see, the magnetic force is just the Lorentz force in which the electric field is equal to 0. Okay, so in some textbook, and this example I've taken from a different textbooks than the one we use for the class. They use Lorentz force for everything, and they just say like when E is equal to 0, there's no electric part of the Lorentz force, so therefore it's the same as the magnetic force.
Okay, thank you so much. Yeah.
Could you go back to the second example we did for a second?
Yep. All right, so there.
Okay, yeah, the next slide. Okay, I'm just trying to find, there was a question that you said E was in like the I direction and B was in the J direction and things like that. And I just wanted to clarify how you figured that out, because I wasn't sure if it was in the question, but yeah. I can't find it on the slide right now.
So in the question, there was no orthonormal basis given to you. Okay, if you read the question, they just tell you a proton is going northward and the magnetic field is pointing top. Okay, so when I made a schematic of the situation, I just north, south, west, east, and magnetic field pointing top, so to like out of the page. Okay, then for the calculation, I have chosen an orthonormal basis, so I can write J hat, K hat, and A hat. Okay, but that's a choice that I made afterwards. Okay, with the given north, south, west, S top, you make the first schematic, and then I have chosen this orthonormal basis for convenience of the calculation.
Oh, okay, that makes sense. Thank you.
Any other question?
Yeah, sorry. Okay,
okay. Yeah, going back to this question that was just asked, like they said the velocity was pointing north and then the magnetic field was pointing up. Is there kind of a situation where like the magnetic field and the velocity points both up because like up is kind of north or something, or we just have to like intuitively know that up is like outward of the page, but there's also a situation
I mean,
where
like
it could point up.
basically, this is a situation that is more or less related to your own experience. Okay, when you're on Earth, okay, and you look north, north is horizontal for you. Okay, when you walk toward north in Saskatoon, okay, you do not walk up and down. You walk on a flat surface and you go north. Do you agree with that?
Yeah.
Okay.
Yes.
So that's what here, like north is horizontal, so that I choose that this is my paper, and up is coming towards me. Okay. And I just imagine in my head that I'm walking from south to north, so up has to be out of the page.
Okay, thank you.
Can you go back to the first example?
Yep.
Yes. Can you show me the answer of part C?
Yes. So for C, yep.
Okay, thank you.
Any other question? Nope. All right. So thank you very much for attending this first lecture, and I see you on Friday morning. Bye. Have a nice day.